Hi there, folks. Welcome back to Chem 12 Solubility Units. For the section 3.9, Removing Water Hardness, I've just posted some links to a few different YouTube videos on the Schoology page. Please make sure you go through these and understand what is hard water and how we go about removing this hard water. Okay, ways that you've probably seen this is if your shower head starts to clog up a little bit. That's usually some precipitates from that hard water, and water scaling, if you will, forming on that shower head. Usually isn't too much of a problem in the cities, as a lot of our water treatment plants take care of this for us. But anybody that's lived in rural areas or has a well, my parents have a well, and we end up having very hard water. And so we need to remove this hardness in order to better be able to use it. So please check out those videos and make sure you respond to the discussion that's also on Schoology for that section. All right, welcome back from that brief interlude. Moving on now to section 3.10, the common ion effect. Okay, now if you're following along in the notes as I've posted in Schoology for you for this section, we've talked about how the solubility of a compound is the maximum amount of substance that will dissolve in a given amount of solvent at a specific temperature. And this is a constant given by KSP. However, all of these values are based on pure water, which isn't all that common. Most water, even that bottled water that you like to drink, does have dissolved ions in it, although usually those values or those concentrations are quite low. Okay, so because of this, if I have a certain ion in the solution, it can have an effect on that KSP. Okay, so this makes solubility dependent on both the temperature and the ions in solution. However, that KSP does only have, is only affected by temperature. Okay, the solubility of a substance will change based on that common ion. However, the KSP value remains the same. Okay, so we can think of this as Le Chatelier's principle, again, in effect. Okay, so the example we have there is if that I've got my magnesium hydroxide, and let's see, we've got this in that equilibrium. Okay, so we've got that solid in equilibrium with both of those aqueous solutions, okay, or aqueous ions. Now, if I add into this equilibrium, say I'm going to add in some magnesium chloride, as we have in that example at the bottom, well, I'm increasing this concentration. So Le Chatelier wants to change that, and in order to change it, if we've increased this concentration, I need to drop that concentration. I'm going to see a shift into this direction. Okay, so by adding that magnesium chloride, I'm adding those magnesium ions into solution, and that is going to result in a lower solubility of the magnesium hydroxide due to that increase in magnesium chloride. Now, that will decrease the solubility by adding that common ion. However, if I add in an ion that would reduce one of these two concentrations, so let's consider adding in some HCl. Okay, now although neither one of these ions is necessarily in solution here, okay, and the chlorine mixing with the magnesium, that's going to be soluble, so that's not going to have an effect. However, it's this hydrogen that we've added in that's going to combine with this OH minus. Okay, so if I add those two together, I'm going to produce H2O. Okay, so what I'm doing here is by adding that acid, it's going to react with this hydroxide, and it's going to drop the concentration of this hydroxide. Okay, and so the system's going to respond then that if I'm dropping the concentration of this hydroxides, then in order to counteract that, I'm going to see a shift in that direction. So I'm going to have more magnesium hydroxide dissolved in order to bring that concentration back up. So by adding something like this hydrochloric acid into this situation, I can then increase the concentration of magnesium hydroxide. Okay, so once again, to decrease the solubility of our compound, I'm adding in one of these two compounds into the solution, and that'll cause a shift back to the magnesium hydroxide, lowering its solubility. However, if I add in something like this hydrochloric acid, which combines with one of these two, then I'm lowering the concentration, and I'm going to increase the solubility of this magnesium hydroxide. Let's take a look at the numbers. All right, welcome back to, let's take a look at the numbers here for this magnesium hydroxide. So once again, we've got that magnesium hydroxide solid is going to form a magnesium ion and two hydroxide ions. Now to find our KSP, we can find that in the back of the textbook or on those data sheets. So we've got 5.6 times 10 to the negative 12. Okay, and our KSP expression here is going to be that concentration of the magnesium times the concentration of hydroxide squared because of that coefficient. Okay, so we have this situation going on here now. And so if I look at part A of this example is, what is the solubility of magnesium hydroxide in pure water? Okay, so I want to find that solubility in pure water. Okay, well, let's see, what am I going to set up here? Well, I'm going to take a look at this magnesium hydroxide concentration, right? That solubility. I have that 1-to-1 ratio, so that is equal to the concentration of magnesium hydroxide. Okay, and our hydroxide concentration is going to equal then 2 times that Mg2 plus because of that 2-to-1 ratio. So to solve for this, I'm going to let my magnesium concentration equal X, and so then my hydroxide ion concentration is going to be 2X. Okay, so I'm just going to take these two values and plug them up into here. So I'm going to look then at my KSP is going to be equal to that 5.6 times 10 to the negative 12. Okay, well that's going to equal my concentration of magnesium, or my value of X, multiplied by my concentration of a hydroxide ion of 2X, but that value is also squared. Okay, so I'm looking here then that the 5.6 times 10 to the negative 12 is equal to 4x cubed. Right, I got my 2x squared multiplied by that additional x I have here. Okay, to solve for x, I'm going to take my 5.6 times negative 12, divide it by 4, and then cube root that resulting value. And so I end up with here 1.1 times 10 to the negative 4 value for my x. And that was also then, sorry for blocking this here, the concentration for the solubility of magnesium hydroxide. Okay, and X was a concentration, so I should then give this a value of 1.1 times 10 to the negative 4 as the solubility of magnesium hydroxide. All right, now after we found that concentration of magnesium hydroxide, or the solubility of that concentration there in pure water, we can now take a look at if we put this into a magnesium chloride solution of 0.1 molar. Now magnesium chloride is that halogen, so we know that we are fully soluble at these concentrations. Okay, so we're going to have this here. And now to solve this problem, we need to kind of take a look at this being an ice chart. Okay, but slightly different ice chart in this situation. Okay, so I'm only looking at those ions, right? Those are the only things that are going to be in the solution that I'm worried about. And once again, this is that ice chart. Okay, well, our initial conditions here is, well, we're looking at this 0.1 molar magnesium chloride, and we're going to add in this magnesium hydroxide and see how that affects things. Okay, so that means that my initial here is 0.10. Remember, all values in ice charts are those molarity situations, right? So moles per liter. So I'm just going to write in the values. I've got 0.10, and since my initial value was just that solution, I have no hydroxide. Okay. Now, just like before in that previous example, I'm going to have an X change in my magnesium, and I'm going to have a plus 2X in my hydroxide situation. And that leaves us then with our equilibrium being 0.10 plus X for the magnesium and a 2X for our hydroxide. Okay, but now if we take a look back at that previous example, this value of X is at most 1.1 times 10 to the negative 4. Now, if we write that out as a decimal, we're going to go 1, 2, 3, 4. So we're looking at a 0.0001. But based on this value here and our two sig figs, we're 100 times lower than, or sorry, 1,000 times lower than the initial concentration. And because of that, we're going to ignore this X when we do our new KSP calculation. Okay. I've said before that we don't do quadratics, and this is how we can avoid that quadratic formula in these situations. This value is going to be so small that we get to ignore it. And so then we look at our KSP. We still have this 5.6 times 10 to the negative 12. That's going to equal our concentration of magnesium, which we have down here then is at 0.10. And then we have our hydroxide as 2x, and so this now becomes 4x squared. Okay, just taking that 2x, plugging into our OH concentration and squaring it. So we now have 5.6 times 10 to the negative 12 is equal to 0.40x squared. Okay. So I'm just going to divide out this 0.4 and then square root the resultant value, and I get an X value here of 3.7 times 10 to the negative 6 molar. Remember, X was representing our magnesium concentration. Okay, as we did in that last problem, right? We just had X, and that makes that 2X. Okay. And so we see even here then that by adding that 0.1 molar magnesium chloride solution, we take that initial concentration or initial solubility of 1.1 times 10 to the negative 4, and that gets changed then by a factor of 100 to go to a 3.7 times 10 to the negative 6. And this is known as that common ion effect. Okay. There's a few more questions for you from the textbook and at the bottom of this page for you to answer. Please check those out and then pop back online later this week for our office hours, which I will post on Microsoft Teams. All right, thanks folks. Have a great day.